Awesome. So thank you everyone for your interest in this second session of the series Quantum Chemistry Calculations with Python. I am the organizer. My name is Vinayak, and I'm a chemistry graduate student at University of Kentucky. And I try to put together things from my research experience and try to demonstrate how Python can be used for various things in chemistry. And one such instance is running DFT calculations. So this series is based on running DFT calculations, and this is the second session. And the session will be recorded, and the videos will be made available on YouTube, and the files associated will also be shared so that you can look at those things again and make sure that you understand if you missed out something. And if you are interested in keeping in touch, you please do subscribe to the channel so that you'll get updates when new videos are posted. So this is the second session in the series. The first session was about input structure generation, and I hope you might have reviewed so you might have reviewed the first session. If not, it's okay. There's not much overlap between this session and today's session. I'll demonstrate some of the things. We'll discuss a lot of things of basis that it'll be a bit of theory as to what is going on, but at a level that could be easily understood without too much of knowledge in quantum chemistry. Okay, and so the next session will be on September 10th, and that'll be the final session in the series where we'll talk about absorption spectra and time-dependent DFT calculations and stuff. And all of these would be interactive sessions. So I'll share the link with you so that you can work along with me. And there is not too much of coding in here, but if you go on to that link, you will see, you will go to the GitHub page, which has the files necessary for us. So this is the notebook that we are going to use, the DFT Basics, and this one is the first session. So you can click on DFT Basics, and it'll open up the thing that we are going to use, and you can click on Open in Colab. So you'll need to have a Google account. It may ask you to sign in, but if you're already signed in, you should be able to get to this page. So if you can open the notebook in Colab, just let me know. You can give me a thumbs up or let me know you're at this point so that we can proceed. Can everyone see my browser screen? Do let me know with a thumbs up or something so that I'm sure that you can see the browser screen. So is everyone able to get this page open? Yes. Okay, cool. So this is Google Collaboratory, an environment where you can run Python stuff. So it's like a Jupyter notebook. And if you are not familiar with this, all you need to do is press this play button to run this cell, and it'll run the code within it. So the first thing that we are going to do is you can click on the run anyway. and it'll run this. So we are going to install some packages. The first package is SCF, and that is what we are going to do or use for running DFT calculations. And RDKit is what we will use for generation. This was discussed in greater detail in session 1, how we can generate the input structures for DFT calculations with RDKit. So we'll generate some structures with this. And geometric is for geometric optimizations that we are going to perform. It's required by SCF to do optimization. So once you click on this, you will see that it'll do some stuff, and finally it'll tell you that installed. So if you're at this point, you have successfully installed the packages that are required for this session. So you were able to install the packages. Do let me know so that we'll know that it's ready for us to proceed to the next step. You can let me know in the reactions, or you can just type it in the chat, or unmute yourself and let me know it's working. Okay, cool. So you see a couple of thumbs up. So let me proceed. So just to recapitulate what we had done in the last session was we started to generate molecule and then run some DFT calculation. So in this first cell, we'll just do that so that we know, we just get an idea of what we are doing. Okay, so we will import RDKit and all these libraries that we want from here, and we'll generate a molecule for a water molecule. And the smiles is O. Smiles is a way of representing a molecule with a string or characters. So we'll generate a molecule. So the first step over here is smiles O, and then this will generate a molecule. And the molecule right now is missing hydrogens. So we add hydrogens. And at this point, there'll be just 2D coordinates. We need 3D coordinates. So this makes it 3D coordinates. And over here, what I'm doing is I'm making one of the bonds longer so that we know whether it's optimized or not. We can look at the geometry and see that what it looks like. And then we finally save the molecule as XYZ file. And once I run this cell, you'll see that we have generated a molecule. And if you click on this files icon, you will see that a water XYZ is generated. And this is the file that you can use for looking at stuff. Okay, so you can download this file if you want, and then use something like Avogadro to view that file. Let's see. So this is the water molecule, and as you can see, one bond is long, and it does not. One of the hydrogens is far away. That's because we draw it a little bit far away. And once we'll see what happens when we do optimization and stuff. But this is for viewing the file. You can use any of the viewers for viewing it. Over here, I use Avogadro to just use the XYZ file. Yeah, and all of this is discussed in greater detail in session 1 if you missed it, but we'll not dwell into this part a lot. Okay. So once we generate the water molecule, we'll run DFT calculation. So what we need to do is we need to create an object for SCF. So the molecule, the way we load it is this line of code. And once it's loaded, we will use some basis set. And in this case, we use STO3G and some functional. These are the parameters that you need for running DFT calculations. And you would put in B3lib and finally say run calculation. So this will give you something called converge SCF energy. And this is where we ended the last session. We got a value for converge SCF energy. Okay. So in this session, what we are going to do is actually see what this is. What is the basis set? How do we choose a basis set? And what is a functional? And what is the theory behind all of that? And what is this energy that we get? And what does it mean, right? So let's get started with understanding what is happening behind the scenes. Okay. So what we are doing, and do interrupt me if you have any questions. You can type into the chat or unmute yourself and ask me questions. Okay. So this is about some basics of DFT and how we interpret this energy and what are the basis sets, what is a basis set and what is a functional, essentially. Okay. So we start with Schrodinger equation, and this is an equation. This is a quantum mechanical equation proposed by Erwin Schrodinger back in 1920s, and it's equation that looks like this: E psi is equal to H psi is equal to E psi, and psi is the wave function, and it's something that describes where your electrons are. R is the electron. If you have a system like this, R is the little r, lowercase r is the coordinates for each electron. The capital R is the coordinates for each nucleus. So once we generate those, once we have the molecular geometry, what we know is the position of those nucleus right now, right? And we can somehow approximate the position of electrons. And for that, we need this basis function over here, okay? So we need to input this somehow and use this H to get energy. We solve this equation to get the energy. And this is the energy that you see over here when it says converged SCF energy. It's this energy. And let's see how it goes about solving this equation. We would need two things, right? So one is the form of H. What does H look like? And what does this look like? So the psi part is actually the basis set, okay? So the thing that we specified here, the basis set, is actually trying to do this part. And the functional comes for this, and that is the equation, that is a way you're going to solve this equation, and that is the Hamiltonian, and that is the functional. Okay. So the functional over here can, if you have a system which is like this, we have nucleus and electrons. So, okay, so you have nucleus and electrons. So you can partition it into some sort of kinetic energy term where TE is the kinetic energy of electrons and kinetic energy of the nucleus. Okay, so there'll be two terms involved. And then this is like considering all interactions that are possible into this. So you have nucleus-nucleus interaction now. So VNN is the nucleus-nucleus interaction, the potential energy term, the Coulombic interaction terms. Okay, and then electron-electron interactions and nucleus-electron interactions. Okay. So any questions so far? So what we have done is the Hamiltonian H, or which gives us energy, given this part, the psi part, can be broken down into different terms, the kinetic energy term and the potential energy term. And kinetic energy can again be decomposed into kinetic energy of electrons, kinetic energy of nucleus, and then all the Coulomb type interaction, nucleus-nucleus interaction, electron-electron interaction, and electron-nucleus interaction. Okay. So once you add this part, there is one approximation that goes into this, okay? And that is called the Born-Oppenheimer approximation. So this approximation. And this approximation says that the electrons are very fast moving. So the nucleus, in a sense, can be assumed to be very static, okay? And if we assume that, you can just say we are just going to solve the equation which involves electrons only, electronic interactions, and not nucleus-nucleus or the kinetic energy of the nucleus, because it can be assumed to be very static compared to how fast the electrons are moving. And once this approximation is in place, the part reduces to the TE, kinetic energy of electron, electron-nucleus interaction, and electron-electron interaction. Okay, and kinetic energy nucleus electron interactions can be modeled easily because you know what is the what is the velocity of a moving electron or some things like that. But the challenging part in this is the VEE. Okay, and the whole idea of solving this is called electronic structure theory. And if you have heard that term, it's because you're going to just solve the electronic part and you use the Born-Oppenheimer approximation. And the challenge here is the VEE part, because electrons are quantum particles. Okay, that's where these things get messier. If they were just like Newtonian particles, or just like big particles which do not have any quantum effects, it would just be the Coulombic interactions between the electrons. Okay, so if you consider Hartree-Fock approximation, that's one way of solving the Schrodinger equation, which says that you can have the Coulombic type of interaction, which is called the Hartree interaction, and also the exchange interaction. Now, this is because of Pauli's exclusion rule, saying that, which says that two electrons of the same spin can never occur at the same place at the same time. So because of that, you have something called exchange energy. Okay. And if you use Hartree-Fock approximation for this, you will end up losing something called electron correlation. It tells you how correlated the motions of electrons are. Okay, and that's one reason Hartree-Fock methods. It's one of the ways we have not discussed what Hartree-Fock is, but it's a way of solving the Schrodinger equation with this approximation, and it fails to account for correlations, and it gives up to 98% of accurate values that you need, but it fails in that 2% where you have the real chemistry involved, which is going on. Okay, and yeah. So any questions so far about this, or something that you did not understand? This is a little bit into density functional and what that function does. Okay. So let's proceed. You can go over this again. Once we finish it, you'll get the big picture of what is going on. So what we can then do is, if you want to compute energy for the water molecule that we have. So in this case, you would need the coordinates for each and every atom, each and every electron in the system, because R over here is the coordinate for those electrons that are involved. So if you are solving, for example, say 10 electron system, if you have 10 electrons, and for that case, we would need to have a 30-dimensional equation, because you have X, Y, Z for each electrons, and if you have 30 electrons, so it becomes, if you have 10 electrons, you have 30-dimensional equation that needs to be solved. And that is a bit time consuming, and all these Hartree-Fock type methods are expensive. So it was proposed, instead of using the actual coordinates of the electrons, let's use electron density. Okay, so electron density at a point will just depend on 3 coordinates, X, Y, Z. So in that case, the solving of the equation would reduce from a 30-dimensional problem to just 3-dimensional problem. And that's where DFT comes in handy, and it's very fast compared to some other better post-Hartree-Fock methods. Okay, so what do you do in this? So what we are doing in density functional theory is we are assuming this. Let's see if I can get this picture right. Okay. Yeah. So we have n electron systems. Like in water, we have we have electrons from hydrogen and we have electrons from oxygen interacting. So what DFT does is it considers the system is not interacting at all. The electrons from hydrogen are not interacting with electrons from oxygen. So all of them could be treated as one electron systems. So you use one electron system, and then you put in this correction called exchange correlation. We'll see what that is. And then once you put in that, if you have the exact density, you can find out exact energy. Okay. And on the right over here is shown how decomposition takes place. So as we saw earlier, we had the kinetic energy term. Okay. And this V external is the interaction between electron and nucleus, which is VNE. So this part, and this is the Coulombic interaction between electrons. And we saw that was an exchange. There was an exchange part. So in DFT, what we do is, because we are assuming electrons are not interacting at all, we move the interaction terms from it, and it becomes a kinetic energy of non-interacting electrons. Okay, and then you have the external energy as it is, the Hartree energy as it is, and this contribution from here, which was missing, is added into this exchange term. And remember, we were missing the correlation part. So all of this becomes something called exchange correlation. And what all of DFT does right now, because we used one of the functionals, and that functional is essentially how we are going to describe this part. All of this, the kinetic energy of a single electron, the external energy, which is electron nucleus interaction, the electron Coulomb type interaction, all of these remain the same irrespective of functionals that you use. And the functional that you are going to use is just the exchange part. So we'll see how that turns out. Okay, so over here is the diagram shown of what it looks like. The exchange correlation just accounts for 8%, but this is where the real chemistry happens. Even though you can exactly find out all the rest of them, there's problem in finding, we have some difficulty in exactly determining the form of this exchange correlation. Okay, so depending on how you solve exchange correlation, we have different functionals, and that's where the functional B3LIP was used. And one way of doing it is just looking at the electron density. So if you just look at electron, if the form of the exchange depends on just the electron density at a point, those are called LDA or local density approximations. Okay, and generalized gradient approximations, instead of just considering the electron density at a point at XYZ, you're also considering the gradient or derivative of electron density, and that becomes a GGA functional. And PBE, if you have heard of one, that's a GGA functional. And it becomes more and more accurate as we go to meta GGA, which considers also the kinetic energy density. And there's a hybrid functional. So what a hybrid functional does is it uses LDA or GGA. You can use any of those approximation. And then it uses Hartree-Fock method to actually get this part. If you remember, the Hartree-Fock exactly gets the exchange part, but what is missing is the correlation. So if you mix some of exchange from here into approximation, you get better results. And those are called hybrid functions. And that is where B3LIP is very handy. And it's a hybrid functional where it accounts for all those exchange part exactly. So the correlation part is little off, and that's where the errors pop in. Okay. Okay. So any questions so far? So all that because the reason we have multiple density functional is because we don't know how to exactly solve the EC part, the exchange correlation part. And there are multiple methods proposed, and all those methods proposed give you different functions depending on how they are going to fit or create that exchange correlation part. Okay, and that's like the big, I would say, take home message I would try to put out there for you. Any questions? And if you want to look at more functionals, you can just look at this by SCF and see what functionals are available. And the images that you saw in this are from this book. And it gives a very nice way of making you understand what is actually going on in DFT. Okay. If you are interested, you can read further. Okay, but T is missing. But yeah. Any questions on this? I know it's a lot of talking in this part, but hopefully next part will be a little of coding where you can see stuff. Okay. So back to the equation. So the equations will be pretty much similar to H psi equal to E psi, but they are called not Schrodinger equation when we do DFT. They are called Concham equations, and it's very much similar to this. Okay. So the density functional part was this, the form of H, right? And now let's look at psi. How are we going to model something given the coordinates? And this is the basis set part that we want to understand. Okay. So, and there's a bit of coding that we can show what is happening behind the scene for this. Okay. So now going to the basis set. So remember we used STO3G in the cell as the basis. So we'll see what it looks like and what it actually does. Okay. So if you run this cell, these are some functions for plotting, and we have the Slater determinant, Slater function. I'll tell you what those are for 1s and all of that stuff. So you can just run this cell. It won't give you any output. Okay. So once you are here, do let me know you are able to run the cell so that we can proceed with what we are trying to do next. So give me a thumbs up or something in the chat so that I know, okay, you are here at this point with me and I've not lost you with the theory part of DFT. So make sure you run this cell and yeah. Okay, cool. So for describing an electron, what is happening is the position of an electron. We have something called wave functions. So the R that we saw earlier, the little R, can be described, and those little are the coordinates of electrons. So that can be described with this equation, which is called a Slater function. Okay, we'll not see what the derivation and all of that stuff is, but for hydrogen 1s orbital, if you want to represent an electron that is in hydrogen 1s, the function looks like this. And we'll just plot it. Okay, when you plot Slater, it's going to plot that function. And what it tells you is how likely is it that you find an electron close to the nucleus, and nucleus is at 0. And you'll see that it's very highly probable that the electron will be close to nucleus. We are talking about 1s electron over here. And as we move away from the nucleus, it's less probable that you would find it over there. Okay. So this is what the Slater function looks like. And if we use this Slater function, we could just say, okay, a 1s electron should use this function for modeling the psi that we have, right? And we could have done that, but solving this equation and doing the stuff that DFT needs to do, we'll have a lot of integrals and differentiation and all of that stuff. Handling this is a bit complicated. So what people have found out is instead of using a Slater function, we could approximate the Slater function with some Gaussian functions. Okay, a Gaussian function looks like this. You have minus R squared dependence over here instead of just R that you saw over here. Okay, so this R square makes a little bit of math easy while you're doing stuff, and your Slater function can be represented as some of these Gaussian functions. Okay, and that is what STO3G is doing. So STO is Slater type orbital, is represented by 3 Gaussian functions. So I can show you what it looks like over here. If you run this cell, you will see 3 things over here. So the 0 indicates which angular momentum it is. So S orbital has L equal to 0. So this is the quantum L that we have. So this is S orbital. So the S orbital of 1s orbital of hydrogen we are representing it by 3 Gaussians. Okay, so this is the alpha value that goes into this equation over here, alpha, and this is the coefficient for that Gaussian. So you have some fraction of one Gaussian, some fraction of the other Gaussian, some fraction of the third Gaussian. Because we have 3G, we have 3 Gaussians, and we can plot those Gaussians. Okay, so over here I do the plotting of those Gaussians, and we'll also see what the sum of Gaussian looks like. So if you click on this, you'll see that the starred one is actually the Slater function. We approximated it with 3 Gaussians. The 0, the blue line, the 1 is the orange, 2, the third Gaussian, the green. So when you sum it up, it looks like those red dots that you have. So you see it's nearly describing those Gaussian, the Slater function that you want to describe. Okay. Does that make sense? Do you have any question at this point? Any questions? So we had a Slater function that describes 1s electron, but using those equations is pretty inconvenient for doing the math. So we use 3 Gaussians to represent those. And once you use those 3 different Gaussians, combine them together, it looks like this. And those 3 individual Gaussian that you use are called primitive Gaussians. And the STO3G, where you sum up little fractions of those, is called a contracted Gaussian. Okay. And this is the plotting of that stuff that we did. Any questions so far? Okay. Let's move on to the next stuff. So if we do this for a carbon atom, we'll see what are the Gaussians that we need. STO3G basis set again. Okay, we have Slater type orbitals represented by 3 Gaussians, and in this we have 1s, 2s, and 2p electrons. So this is the s orbital. So this will be the 1s orbital. We are representing each of them with 3 Gaussians. This is the 2s orbital. So if an electron is in 2s orbital, we'll use this representation for doing it. If electron is in 2p, we are going to use these 3 Gaussians to represent that thing. Okay, this is the wave function generation. So this is for carbon. You can change it to whatever element that you want, and you will see different Gaussians put in there. And this will be the value of the exponential term, E or alpha, and this will be the coefficient for each of the primitive Gaussian that you're using. So this is good, but you're using 3 Gaussians everywhere, and it may not be so good in describing the core electron density or the valence electron density. So if you go back over here, you see that this part is not so well described over here. So we would need some ways to describe it more better. So what people have done is they try to split the Gaussians for the valence electrons. Okay, and once this, what do they mean by splitting it is, so for example, this is one type of basis set which is called STO3G. No, sorry, 321G. And what it does, it uses 3 Gaussians for the inner shell or the core electrons, that is 1s if you look for carbon, and the valence shell is 2s and 2p. So those valence shells are, instead of getting 3 Gaussians each, we split them up, and we'll say we use 2 type of Gaussians to describe one set and 1 type of Gaussian to describe other set for the valence electrons. So if you load this, the 0 is the inner shell, the 1s shell. You'll see that we just have 3 Gaussians for them. But the outer shell now, because we split it into 2, we have, this is the 2s shell. So 2s shell will have 2 Gaussians of one type and another Gaussian of another type. And the p orbitals, the 2p, again will have the same thing because we use 2 and 1 Gaussians for the valence shells. So 2 and 1 Gaussians for the valence shells. So what this does is it describes the inner shell more accurately, because we just don't use 3 electrons. We can use like the 3 Gaussians. So we can even use 6 Gaussians, and we can see a comparison of how those differ. So the blue one is the STO3G, where we just use 3 Gaussians. And if we now use 6 Gaussians, you see that it more accurately describes the electron density of 1s orbital. Yeah. So this is how the split valence basis set comes in, where you have just two type of Gaussians for the valence shell. It's called the split valence or a double zeta basis set. And then you can go into triple zeta basis set, where you split it into 3. You say like 6311G is one type of basis set, which is a triple zeta basis set, where you have 3 one type of Gaussians and then 1 and 1 contracted Gaussians. If you just look at this, so you'll see that now the 0, the 2s, has 1, 2, 3 different types of contracted Gaussians, and 2p would have different types of Gaussians. So as we go on increasing the number of Gaussians in the basis set, you try to make it more accurate in describing your electron density. And then sometimes if you think of a s orbital, you want some polarization into it. So some polarization, like hydrogen is spherical, you just need to make it like this, little bit spread out. So we can add polarization terms. And if you use a star, what happens is if you have that star in front of it, they are called polarization functions. And it adds a function of higher L value. So over here, we have the highest L value is 1, which is 2p. So for 2p functions, it's going to add a 2p, yeah, it's going to add a 3D function. And because D functions are more polarized than P functions, so if you add D functions to P functions, it will be more polarized. So that's how it's combination of functions. Okay. And you can add it to hydrogens too. And if you just add star, it's not going to add polarization to hydrogens. And you see it's 0 and 0 because we use 631G. And because it's just 1 electron in 1s, it's the valence shell. So we are going to just use this part of it and not the 6th part of it, because it's not a inner shell, it's the valence shell. So you see 3 and 1 type of Gaussian. But if you start with the polarization, you'll see that S, now p orbital is added to this, so that it's not spherical anymore, it's a little bit polarized in some direction. So you add the p orbitals. Okay. So any questions so far? So this is all about the theory. So we looked at how H psi is equal to E psi. We saw the H part, which is the density functional for DFT. And then we saw the psi part, how we are going to use the basis sets for this. So if you go to basis set exchange, you will see a lot of functionals. And we use the 621G. And you can see how many elements those are valid for. So if you want to model something in this is not a good basis set. So you'll need to see which is a good basis set for you to model a particular atom using DFT, because not all the functions are described for it. And we saw 6311G, and usually takes in all of these things. So any questions? Yeah, so there's one question, which is about using Dunning type basis, which is called DEF2 SVP. So those are another type of basis sets, which are called DEF2. So if you look at those basis sets, you can just type in the same thing over here, which is DEF2 SVP. And this is one type of basis set. And this is a split valence basis set. And that's the first thing that we talked about, right? So you are going to split it. And this is the splitting that helps. Let's see if I come. You'll see the splitting flat pattern. So this is where you're going to split it. So it's like 6, 1, 2, 3, 4, 5. Okay, so 5 for the inner ones, and then you're going to split it. So it's a split valence type basis set where the outer electrons are split again, like 3 and 2, 3, 1 or something. So you can use the triple zeta basis set like 6311G. So TZVP. This will be the triple zeta basis set. So all of these can be used for running DFT calculation, and it depends. I use the Gaussian, so these are also like Gaussian approximations for it, but they have different PV factors, right? So that is where basis set comes in. So you have different sort of ways of approximating it, the values that you put. So all different basis sets will have different values and different ways to model electrons around the nucleus. And again, this is all about modeling electrons around the nucleus, how we are going to model it, so that we can put into that equation. So I hope this helps. So you can just load any of the basis set, at least in SCF. So there's another question, which is, when do we use STO3G and 31G? Okay, so STO3G is the minimal basis set, and there's something called, maybe I should have put it in there. It's called Jakov's ladder. DFT. So if you look at this, it tells you about basis set and functional. So if you go with as big as a basis set, like as big as a basis set, you will get more and more accurate values. But there's a compromise with compute time. So if you use a very large basis set, it'll be accurate, but it will take more time. And that is where your requirement comes in. So whether you want to use, if you're doing it for big molecule, let's say you're doing it for protein, maybe you can use STO3G basis set because it's very small, and you can get some reasonable estimates. But if you want to get more accurate estimates, you would need to use like 31G, for instance, right? So just increasing the basis set increases your approximation or accuracy of the calculation that you're doing. And you can try it with the examples that we have at the bottom, and just try changing the functional and the basis set and see how good accuracy you get. So at the end of the day, choosing a basis set is more of an art. There's no science, I would say, into it. And other than saying that the bigger the basis set, the better the accuracy for us use for a given set of functions. Okay, I hope that helps. So there's another question, which is about what basis set will you recommend for DFT calculations involving halogen bonding interactions, which has a lot of polarization characteristics. So it depends. What I would do is I would go to a basis set exchange and see which of these basis sets have the halogens that I'm interested in. So if I'm using 6311G, you would see that there's no bromine and chlorine involved in it, right? But 631G has bromine and chlorine involved in it. And this D and P is the polarization part. Okay, so there are different ways of doing it, but these two functionals are essentially the same thing. Basis set are essentially the same. So D is adding D orbitals to P orbitals, and P means you're adding P orbitals to S orbitals. That's only for hydrogen part of it. So I would see which of them is involved over here, and I would just use that. And I think if you are doing polarization and all of that, what will be more critical is the functional. And if it has halogen bonding interactions, your functional, the H part, right, of the equation should be good enough to model those interactions. So all of that depends on the exchange correlation part. So I would maybe use a higher function, like a functional, better functional, which people use for defining all these interactions. So I hope that answers that question. So there are two things, right? So one is the functional, one is the basis set. Basis set, just to model the electron density. The functional actually get the energy from this density that you have. Sometimes functional is more important. Okay. So there's another question. Are these numbers in Pi SCF database? So I think, so I'm thinking the question is referring to these numbers that we see in the Gaussians that we have. So the alpha and the C values. And I think those are either gotten from the basis set exchange, or they are stored in Pi SCF, but it should be some, if you are able to download this basis set, I think, yeah, you can download in various formats. You will see those numbers in this somewhere. And those will be for all those electrons. And right now, what we did is we just loaded it for carbon. You can just load it for hydrogen and see what it looks like and all the different things. Yeah. Okay, that's good. So, okay, so we just have 10 more minutes. So we'll go into the next part, which is geometry optimization. What we first did was energy, okay? And in that, what we had was we got some form of the density, the rho, and we had used a basic exchange correlation function, which is B3-lib. And we evaluated the Concham equations. Concham equation looks similar to the Schrodinger equation, but from this you get you get the energy and new density, and we had some convergence in it. So that's the reason it said converged SCF. So it's this part that converged and gave us the energy that we needed. Okay, so these E values, and we'll see in the next session how to get those E values, the little E values. And those are actually the orbitals that you can think of. And we can get HOMO value and LUMO value and all of that. But that's next session. So it did just this part. And if you look at the structure, it'll still have the bond missing. The hydrogen was too far away. So what we can do is, once we have energies, we can calculate forces, because you can take the derivative of energy, you get the force. And you can then see what are the forces acting on it. You can move the atoms a little and then put a convergence on forces that you see. So this part is called the geometric optimization. So a geometric optimization will run a SCF cycle. Okay, this is the self-consistent loop. Or self-consistent field, as it's called. So you're going to run the inner one so that you get converged electron density. Then you calculate forces, and then you continue the loop. So in this case, let me just run it for the water molecule that we had, and I'll show you what it looks like, right? So let's start with the output over here. So you started cycle 1, and these were the initial coordinates that you had. Right, and then you get the converged SCF because you ran the inner loop where you generate the electron density, and you find the energy. So this was the inner loop, which gave you converged energy. From this energy, now you calculate the gradients or the forces in each direction for those atoms. And now what you want to do is minimize these forces. So you move the atom a little, and then you get new coordinates in cycle 2. Right? So your earlier coordinates, if you look at, is very different from this coordinates. So again, you run a SCF calculation. SCF calculation is converged, and then you get some gradients again, calculate the gradients again. And you have some sort of gradients, and then you move the atoms again. So you keep doing this until you'll see the last cycle. Let's see, where's the last cycle? Yeah. So the last cycle, the gradients are very, very small in each direction. So this is where your geometry optimization would end. And it'll consist of SCF cycles as well as gradients and moving things. Okay. And this by default has some cutoff parameters, and so those cutoff parameters, yeah, you can save this XYZ, and let's see whether it was really optimized. So you can just click on download. It should download it, and let's see whether it and then put it into our cat. See. So we had that bond that was missing, and now it's optimized. It's doing stuff, and we get the optimized structure. But behind the scene, that is what is happening, right? So, and you can set off convergence parameters, how quickly you want the energy change to be converged and all of that. I would recommend you look at the manual for any software, any electronic structure package you're using, and see how they are converging. But this is just to demonstrate that this will converge more quickly, because cycle 1, it did this, cycle 2, it did this, and cycle 2 itself, it stopped. The reason being, we asked it to stop with these parameters, cutoff parameters. It may not have optimized it. So you can look at saving this coordinates and seeing whether it really optimized or not. Any questions on that? Any questions on optimization? Okay, one question. So how would I optimize a molecule with the solvent like water in Python? So it's I would say there are two parts to this question. One is how you're going to optimize a molecule with solvent, and the other part is in Python. So optimization of molecule is dependent on the input structure that you provide. So input structure has a water molecule, it will run the optimization calculation, and the optimized results would depend on where you actually place the molecule. It's not going to give you absolute placement. If you just place a molecule far away, it may just be there, and you may not actually show the interaction that you want to observe. So initial structure generation, that's the reason, is very critical for DFT calculations. If you want to do it with Python, you can use PySCF and make sure the input that you provide has some water molecule into it. So you can take a PDB structure, if you something like that, and make sure there's a water molecule close to it, and then give the XYZ to this PySCF, and it'll run the calculation. So there are other ways of doing solvent, and we'll talk about that in the next session, where we do absorption calculations with different solvent and stuff. So one way is putting explicit solvent into it, and the other way is something else that we'll discuss next time. Okay. I hope that helps. So there's another question. Can we split level for different atoms? Yeah, I think the split levels, by that you are referring to the splits for each atom, or each type of atom that is involved. You can actually split it for each type of orbital too, I think. Depending on what basis set you use, you can split s orbital differently and p orbital differently sometimes. And there are ways to doing it. So you can specify which atom needs what type of basis set. So again, there's no need of using just one basis set for the entire molecule. If you want to model carbon with the 631G and hydrogens with STO, you can do that. Okay. So there are ways of doing it. I would refer you to the manual. If you're using PySCF or any other software, you can look at the manual and see how they recommend you to doing that. But yeah, we can use different basis set for different atoms involved. So this is the last part, which is frequency calculations. So the thing that we just did may or may not have been converged, because we had set some cutoffs for it. So that's the reason we usually check it with frequency calculations. So your converged structure may have been here at the local minima, at the local maxima, but actually you needed a local minima. But at both these points, the derivatives are 0. Okay. So f prime x will be 0 at this point, as well as this point and that point. So it can be stuck somewhere, but you actually need to know whether it's a maxima or it's a minima. So in that case, frequency calculations are what will help you to know whether it's a minima or maxima. So what a frequency calculation does, it finds the second derivative of those, and it turns out the second derivative that we calculate is actually frequency. So if you do a frequency calculation, at this point you are going to get an imaginary frequency if you are at maxima, but if you are at a minima, all the frequencies should be positive. Okay, so that's one test for getting actual convergence. So once you run this calculation, so what we are doing here is we are using the optimized water molecule, STO3G basis set, and B3 lip functional, and we are running the Hessian, and Hessian gives us a way to compute frequencies. So if you run this cell which says frequency analysis, it'll give you frequencies, and you see that all frequencies are positive. That means the structure was optimized well, the first structure. But if I just do it for water molecule, you'll see that SCF converged and all of that. But if we look at the frequencies, you will get a complex number here. All of those are complex, saying that this is not a good structure, right? So yeah, that's the end of the things that I have had for you to look at in this tutorial. There are exercises here at the bottom. So you can try running the frequency for unoptimized water molecule. And so you can see what, and I showed you what happens, but you can try to reproduce this spectrum of frequency with different basis set and different functionals, and see what functionals give, what functional or what basis set gives you better results. Okay, and at the end we have a survey. So do submit this so that I can know what things I can improve in the next workshops that we have. Okay, so let me go ahead and stop recording.